Welcome to Unit 7, Cartesian Vectors, Lesson 3, Application of the Dot Product. Our first example will be find the work done. So this is an application of the dot product. We saw this example yesterday. I'm just going to rehash it today. Tanner has entered the wheelchair division of a marathon race while training. He rides his wheelchair up 300-meter hill. So he races up 300-meter hill with a constant force of 500 newtons applied at an angle 30 degrees to the surface of the hill. So find the work done by Tanner to the nearest 100th joule. So first of all, we have the hill, which is 30 degrees. It's right there. We know that the displacement is 300 meters, and we know the force is 500 newtons. So for this, I can simply use this formula here. Work is equal to the displacement times the force, magnitude of the force, times cos of the angle relative to the object. So here we'd have W is equal to, here our force, or our displacement, sorry, is 300, so 300, bracket, force is 500, cos of the angle, which is 30 degrees. So here we get W, the work done here is 1299, and it's just needed with 100, so 129,900 joules. So I'd write a therefore statement. Therefore, Tanner did about 129,900 joules of work on the wheelchair. If you want to see a proper therefore statement, there is one on the class website. All right, next question is find the angle between two vectors. So here I want to find the angle between the vectors of each pair, so G and H. Now we know that G dot H is equal to the magnitude of G, magnitude of H, cos of theta. So I can rearrange this formula by isolating for cos theta, by dividing both sides by magnitude of G, magnitude of H, and I get this formula here. So this formula is actually very valuable when wanting to find the angle between two vectors. So here we go. I can do this. So I will get cos theta is equal to the dot product. So here I'm going to have 5 times -3 plus 1 times 8 all over the magnitude of G. The magnitude of G here would be square root of 5 squared plus 1 squared times -3 squared plus 8 squared. So there we go. When I have this, I've got cos theta. Put this in my calculator. I get here, just go down a little bit here. Cos theta is equal to, the numerator is going to be -7 all over square root of 26 times the square root of 73, 3 squared plus 8 squared, and I do cos inverse of that in my calculator. So here I get theta is equal to 99 point, we'll go to 1 decimal place, 2 degrees. So the angle between them, by the way, really important here, we can see the dot product is negative, and if the dot product is negative, that means the angle has to be between 90 and 180, and here we can see that it is between 90 and 180. Again, one of the properties of the dot product. We can do the same thing over here. So here I want to find the angle between vectors S and T. So here I would have cos theta is equal to the dot product on the numerator, so it's going to be -1, -4 plus -5 times 3 all over -1 squared plus, -5 squared, and then also -4 squared plus 3 squared. And so when I do this, the dot product here is equal to negative 11. So again, I know that my angle is going to be between 90 and 180. Here I'm going to have the square root of 26, and here I'm going to have the square root of 25, so a cos inverse of So cos inverse of negative 11 divided by bracket square root 26, square root 25. So here I get 115.56 degrees. So again, this formula right here, really useful. Now we can find the angle between any two vectors, especially in Cartesian form. The projection vector, so this is an application of the dot product. A vector projection is like a shadow. The projection of V on U can be considered like the shadow of V cast on U. We're going to see that on the next page. So the projection of V on U can be written as, this is quite important, like this. So always V is on that same line as projection, and then U, it's casting on U, and you can see that's going to be subscript there. Alright, so here I'll show you some examples. So the first one, projection of V on U. The angle between V and U is between 0 and 90. So here's my angle V, I'm projecting on angle U. And so this dotted line here is that projection of V on U, and you can see it's like a shadow. So basically this is protecting it. The sun's rays are coming down like this, and so anything underneath it will have a shadow, and so here, this line right here is my shadow. The projection of V on U, the shadow is the vector component of vector V, so it's a vector component of this one, and in the direction, and you can see it's actually the horizontal component of that, and it's in the same direction as U. The two formulas here, if I want it in geometric form, it is a projection of V on, the magnitude of projection of V on U is equal to the magnitude of V cos of theta, and again that is just the horizontal component of vector V. The projection of V on U in Cartesian form is U dot V over magnitude of U. If the angle between V and U is 90 degrees, you can see here, here's vector V, here's vector U, there's nothing protecting it, there's no shadow here, so here there is no shadow, and the projection of V on U is actually the 0 vector, so that means the magnitude is, of course, 0. The last one, if the angle is between 0 and 90, so here we go, between 0 and 90, then I can see here's the projection of V on vector U, here's the shadow being cast, so here we can see that the projection of V on U, the shadow of the vector component of V in the opposite direction of U. And so if we look here, projection of V on U, if the angle is between 90 and 180, see it's negative here, negative here. With this one we don't have to worry because the cos of anything between 90 and 180 is negative, so I really don't need to put that negative there. Or sorry, I do need to put the negative there to make it a negative times a negative, so it gives us a positive. And same thing here, you'll find that the dot product is negative, so that extra negative there will just give us a positive again, because the magnitude is always a positive value. Alright, we'll do a few examples here. So here, determine the magnitude of the projection of the first vector onto the second vector. So here's U and V, so I want to project U onto V with an angle of 50 degrees. So here, if I want the projection, the magnitude, the magnitude of the projection of vector U on vector V, this is equal to vector U, the magnitude of U, cos of the angle, and so here I'd have 5 cos of 50, and so here I would have the projection would be 3, the magnitude of the projection would be 3.21. This one here, so I want the projection of P onto Q, so here the magnitude of projection of vector P onto vector Q is equal to P, magnitude of P, cos of 120. And again, because my angle is bigger, negative here. Again, that is just, I will get a negative here, so that means I get a positive. And so here I'm going to have, put that in my calculator, I get 10. And again, why do I put a negative there? Because this angle here is bigger than 90, and so I got to put a negative there to get that double negative, so I get a positive value for magnitude. Finally here, projection of D onto C. So I want the projection of D onto C. The magnitude of that, sorry. The magnitude of D onto C. And this is equal to vector D dot vector C all over the magnitude of C. So I'm going to do D dot C first. So D dot C, the dot product of D and C is equal to, you're going to have 2 times 1 plus, and you're going to have negative 3 times 4. So this is actually going to be 2 minus 12, which is negative 10. So because my dot product is negative, what I'm going to do here is I've got to put a negative right here. Again, why? Because the dot product is negative, and I get that double negative to give me a positive. So here I'm going to have negative 10 numerator, magnitude of C, so it's going to be the square root of 1 squared plus 4 squared. So this is going to give me, I ran out of room here, so I'm just going to go here. The projection, the magnitude of the projection of D onto C is equal to 10 over the square root of 17. I'm going to do example 4 on a separate video, so we'll stop here for now.